Hello everyone, my name is Omer and I'm an embedded systems engineer here at Erlang Solutions. Today we're going to talk a bit about the actor model applied to Raspberry Pi and the embedded domain. The stuff I'm going to talk about generally aren't Raspberry Pi specific, you can apply it to any other embedded boards. And in the agenda we have the current state of embedded systems, what are we dealing with at the moment, what are the tools, what methodologies we follow, and then we'll talk a bit about the actor model without going into too much maths. And then I'll talk you through the Erlang embedded project that we have been working on for the past couple of months. And then we'll look at how we can develop and actually model embedded systems using Erlang. And I'll mention a few of our experiments with the Raspberry Pi, and after that we'll talk about the future and some questions and answers if you have any. Before I start, can I get a show of hands or of you who have worked with embedded systems before?
Does Raspberry Pi count?
Raspberry Pi does count. Good. And how many of you are familiar with the Erlang and actor model in general? That is quite a lot of fans. I might skip through those concepts quite quickly, since it's a savvy audience. Okay, so what is an embedded system? Careful. So an embedded system, well, the terminology embedded systems is quite muddled, unfortunately, so we don't have a clear-cut definition. But the infinite wisdom of Wikipedia states that an embedded system is a computer system designed to do one task specifically, often with real-time constraints. Unfortunately, your phone, because of the architecture it uses, could be an embedded system, but it is not, because you can do pretty much everything here. I mean, you can draw stuff on it and email. So the sort of embedded systems we're going to look at are the sort of embedded ARM class devices that can run Linux and any other operating system. So before I get to that, C is still the lingua franca of the embedded world. Just to sort of make the point that most of the embedded engineers are not functional programmers, they're not us. So after we have a look at that, the different ways of dealing with embedded systems, the first one is the bare metal methodology. You don't have an operating system or any high-level abstractions that you have with, say, Linux. Generally, this type of coding implies that you deal with register-level operations on peripherals. The second class of, and the architectures used in these sort of setups are generally 8 or 16-bit devices. You then have the real-time operating system-driven systems. These are generally used for mission-critical systems or medical equipment. They do provide you with certain guarantees, such as scheduling guarantees and sort of jitter guarantees and so on. And then we have the embedded Linux world, which is essentially a slimmed-down version of the desktop Linux that we use. But the main difference being that you have hardware interfaces you have to deal with. We're going to focus on the R2S and the embedded Linux kind of devices and not worry about the bare metal for the sake of this presentation. So, real-time operating systems do give you the notion of tasks, and these are your compositional units that you use to break down your larger systems into. You can group them together per functionality and then create subsystems, etc. And the messaging between these sort of tasks, these tasks happen via operating system supervised inter-process messaging, which usually happens via shared memory. And you have to use mutexes, semaphores, locks to access hardware peripherals. Otherwise, nasty things might happen. For instance, if you have many tasks trying to access, say, one GPIO pin, then that can potentially be very dangerous. So in the software world, if something crashes, the consequences are not fatal. But say if you have a robot controlling sort of safety equipment or something like that, if it crashes or if a pin gets out of control, then potentially you might kill someone with it. So security.
Hell yeah.
Yeah. Well. Yeah. And you also have different types of scheduling in real-time operating systems. The most common ones are either preemptive scheduling ones, which lets you do event-driven programming, or you can have a simpler round-robin kind of structure where your tasks are processed on a time multiplex basis. So embedded Linux is not a new concept. It's been around for quite some time now, but it's becoming more and more popular due to the abundant supply of cheap hardware that we have today. So some examples to that would be Raspberry Pi, BeagleBoard, BeagleBone, Gumsticks, and also a flurry of boards inspired by the Raspberry Pi. And yeah, I mean, getting started with embedded Linux today doesn't cost much money, whereas a few years ago, not in the distant past, you would spend literally hundreds of pounds to even get started with these sort of development. It is a familiar set of tools for software developers, so since it's Linux, you can use your favorite scripting language or compiler or toolchain, but it is actually quite a different territory for embedded engineers who are used to, say, RTOS concepts. So you can't directly translate an RTOS application to the Linux world without having to rewrite majority of it. So you can, of course, use threads or other stuff to emulate the tasks, but that means you have to change the way your communication works, etc. And the device driver framework is pretty horrible. So in order to do hardware interfacing, you need to dive down into kernel modules quite often because the documentation is horrible and it doesn't quite work the same way on all the platforms. So what sort of challenges we're dealing with in the embedded world at the moment? Our applications are getting more and more complex, and to serve those needs, we're getting more and more complicated system-on-chip platforms that have millions of things embedded into them. I'll have a slide on this later, but the complexity of the chips is just ridiculous. And we now have this thing called the Internet of Things, which means that all our embedded systems are becoming connected and distributed. We didn't have to deal with these sort of issues back in the days where we were simply employing RTOSs to do things. And it's 2012, so time to market is a big issue. So learning new tools or adopting a new tool chain is quite dangerous when you're fighting to get your product into the market. So we have to find ways to reduce the gap between the methodologies you're used to and the new methodologies you're going to adopt in your products. And we also have the multi-core and heterogeneous devices that needs different methodologies to your single, essentially, for loop with interrupts. So the actor, since everyone in the room is quite familiar with the actor model, I'll quickly skim through these slides. But the actor model is, again, not a new concept. It's been proposed in the 1973. It has roots in distributed systems and, funny enough, artificial intelligence. So actors are specified as the universal primitives of concurrent computation, and they're essentially building blocks for distributed and modular systems that you can build upon. They are, in their essence, quite self-contained and atomic. They have no side effects, and they don't have shared state. So, and they're also implemented in a variety of programming languages. Today I'm going to talk about Erlang, but you can get them in Java and Ruby and even C++ apparently. The interesting,
if you want to hurt
if you want to hurt yourself, yes. The interesting bit that deserves its own slide is the communication happening between these actors. So they use asynchronous message passing to communicate, and they have a notion of a mailbox. And messages are processed in the order that they're received in. and because they're all individually separated, isolated, you can partition your system in a way that if one part of your system goes down, it won't hurt the others. I will talk more about that in a few more slides. So the operation of the actors are quite limited and well defined. So they can only do 3 actions. They can either do local decisions in their process or change their internal state. They can spawn new actors to deal with the data sort of coming in, or if they want to do other operations that they can't accomplish in their own state. And they can also send messages to other actors, letting them know that something has happened, or if they want them to process something. So a simple example would be to have, say, an actor that performs some calculation. It receives a message with a set of values that it needs to calculate. And then it may decide to spawn or create new actors to deal with subsets of this data. And once these new actors spawned by the sort of main actor do their calculations, they can then return their results back, and the main process can then collate and collect those results back and send it to the original requester. Now, if you paid attention, you might have seen that that was not in sequence. There is no guarantee that the messages will arrive in a sequence, which is one of the downsides of the model, unfortunately. So, one of the main limitations of the model itself is that there is no notion of inheritance or general hierarchy mentioned in the system, so you're pretty much on your own to create your system hierarchy. And languages and libraries do implement their own versions of this hierarchy structures. The synchronous message passing can be problematic for certain applications, so you can, because of the ordering of the messages are not guaranteed, then you can't apply this model, unfortunately, to all the applications. Having said that, I can't think of many applications that will be affected by this in the embedded world. And another problem is that the abstract, because the definition is quite abstract, it may lead to inconsistency in larger systems. So you can choose to treat, say, every integer in your system as an actor, or you can choose to use, say, a larger process collection, or say an Erlang process to be an actor, and then structure your system around that. So fine-grained, coarse-grained argument does play a big part in this system. So the Erlang Embedded project has been going on for a couple of months now, and it's a partnership between the University of Kent and Erlang Solutions, and we're investigating using Erlang as part of concurrent embedded systems. We have been playing around with different platforms. Raspberry Pi has been one of our main platforms, and we're developing a set of tools and methodologies and creating sample examples, sort of use cases and sample applications to hopefully convince people that Erlang does work in the new sort of challenges that we face in the embedded systems world. If you want more information, you can go to erlangembedded.com, or we have a Twitter account as well. Is it just me? I'm melting here.
Just you.
Thanks. Thank you. No?
Just experience a kernel panic.
Kernel panic. Thanks. So, again, I will go through these slides quite quickly since we all love and use Erlang. But why we chose Erlang? Well, since the talk is about the actor model, Erlang does implement the actor model rather well. It's also been used at many companies, and in fact it was originally designed for embedded systems. So Ericsson used Erlang in their telephony exchanges or telephone switches, which by their nature are embedded systems. It also has support for concurrency in distributed systems out of the box. You don't have to do anything extra with it to create different nodes and different networks and communicate with them. And it also has certain features like links between processes and supervisor hierarchies, etc., that lets you create robust systems very easily. There are other features, but I'm pretty sure we're all aware of them, so I'll skip it. So Erlang has simple and consistent error recovery and supervision hierarchies that can be employed to structure systems in a way that failure within subsystems don't cause a massive crash across the system. This partly is a feature of the actor model, because all the actors are isolated in their own sort of little environments. And another interesting feature that is quite relevant to embedded systems is the dynamic reconfiguration aspect, i.e. the hot code loading. And you can link processes together, and in the event of a failure, they can let each other know that something has failed. Again, going back to the topic of safety in embedded systems, this is quite important. So if you have a GPIO controller or a supervisor, you should know about individual GPIO pins or GPIO controllers failing, so that you don't write to them or you don't try to read from them and get data values. So in this sort of scenario that I've mentioned, your GPIO controller will be trapping exits from all these external controllers that you might be employing in your system. Also, we all know that let it fail is our mantra or our ideology in the Erlang world. This has the added benefit of not having fluff in your application code. So you can get rid of that and abstract it away into modules that can deal with the supervision of the system, which leads to cleaner code and ultimately better testability and even code reuse.
Less code.
Sorry?
Less code.
Less code.
There was a study done by Jan Henry, who used to work for solutions, that you end up with a fourth of the code of a similar system written in C++. So it's less code, which is good.
Yeah.
C++.
Let's not talk about C++. We're having such a good evening. Yeah, it also provides supervision hierarchies, and in the embedded world we have this notion of watchdogs, which are, on their sort of primitive form, they're timers. And if your system doesn't respond within a fixed period of time, they kickstart the system and reset it to a known state, and you resume operation from a safe known point. So by employing the OTP supervision hierarchies, you can essentially create mini subsystems with supervisors that act as their watchdog. And if they don't behave, you can restart those processes and then hopefully continue the operation of your embedded system from a known and safe point. So this is a very simple example of how you might have multiple supervisors and multiple worker nodes. Very abstract example, I must admit. And finally, Erlang does have very good support for implementing external interfaces or talking to external interfaces. C is here to stay. There's no disputing that. You can't convince all embedded engineers to ditch C entirely. Some of the hardware drivers or even some of the interfacing bits will be written in C. And that is okay, because that's one of the main features Erlang was designed around, I think. When they were designing these original systems, they had to interface to external C code. So we have the notion of native implemented functions and port drivers to link external bits of code into the Erlang runtime.
Ask the question.
Sure.
How, for when you're running Erlang on a Linux platform, how well implemented is the POSIX interface inside Erlang? I mean, from Raspberry Pi, I mean, you can open ports and sockets and files and TCP and everything else.
Yeah, you can use, I mean, if you're just talking over sockets, etc., you can use Gen TCP, Gen UDP, and directly talk with them. Or you can wrap them around a NIF file, essentially, and then you can directly call your code from within Erlang. without having to resort to using sockets and so on.
Okay.
I have some examples I can show you later if you want. So, all things considered, Erlang, we believe that Erlang could be the maestro or the orchestrator of your connected and distributed embedded systems. Let's talk about Raspberry Pi. Raspberry Pi is a very interesting project, and I'm sure you're all aware of it. Some of us do have our own Pis and robots, which is pretty cool. So, in essence, it's a small computer system with a 700 MHz processor and 256 megabytes of RAM. That's not the important bit. The important bit is that you can buy this for $35 or 20 odd pounds. And the fact that it's so cheap means that I think up to this point they have sold somewhere in the region of 400,000 boards, and they were talking about selling up to 1 million units until Christmas. It is very exciting because it's an embedded Linux board that will end up in some enthusiastic hackers' hands, and the possibilities are truly endless. I mean, we have a robot from our friend Simon over there, and a lot of people are doing some extremely cool stuff with it, and that is exciting. And we've been playing around with the Raspberry Pi. This is a sort of very basic buggy that we have been playing around with, developing our own little hardware modules, etc. And most importantly, Raspberry Pi Foundation is a non-profit, well, it's a registered charity, and their mission statement is to get this board into the hands of school children. Now, if we can provide a useful set of tools that explores this sort of actor model and concurrent programming and hardware interfacing using these higher level constructs, that means that these kids who are future engineers and programmers will learn these concepts now. And when they get to become programmers, they can say, oh, I've heard of this thing called the actor model or Erlang. And hopefully, I mean, since we are heading in that direction, we need to teach people how to deal with concurrency and parallelism. That might come in handy, we're hoping.
You got the Erlang package accepted on the Raspberry Pi, didn't you?
Not yet, no.
Not yet.
No. But yeah.
Sorry.
So yeah, we have our Raspberry Pi package, by the way. If you have a Pi and if you don't want to compile it on your own, or if you think that the version Debian has is quite old, you can go to erlang-solutions.com and download our Raspberry package. We will be creating a slightly leaner and smaller version of our packages in the near future, and we're hoping that might get included in the default distribution, but nothing is set in stone yet. So if you look at the Raspberry Pi as an embedded platform to experiment with, you have the general set of peripherals that you can find in any other embedded Linux board. You have GPIOs, serial UART, I2C, SPI, I2S, if you want to do audio codec and other applications. And you also have PWM as well. So let's look at an example on how we can abstract the hardware interfacing into actors and how we can implement them in Erlang. Let's say we have a process called process A, and we have a physical GPIO pin 17. We can implement these processes so that we can directly talk to the pin and initialize it. So let's say we want to initialize it as an output and bring it to blink a few LEDs or blink the LED with it. And we can send messages down it, and that might talk to an if to actually physically set the registers and so on. But the problem with this approach is the typical problem that you have in embedded systems: access control and mutual exclusion. What happens if we have many other processes writing to it at the same time? Now, because the actor model does have a mailbox, this sort of registered twiddling won't happen real time, but that means that if we send it sort of different state messages, the pin might be toggled on and off or low or high quite quickly. For an LED that might not be a problem, but if you had a motor or a device that didn't like being toggled really quickly, that might cause a real problem. So the way to get around this problem is to create a, so this might be quite dangerous. The way to get around this problem is to create these proxies, hardware proxies. So this is for the GPIO, but you can think in the same terms for other protocols as well, I2C, SPI, and so on. So you can send a message to the GPIO controller to initialize a pin, say 17 as output, and that can spawn a new actor or a new process, Erlang process. So now instead of having direct access to the pin and potentially causing problems, you can talk over this proxy process and then set the state and so on. What this means is you now have someone in charge enforcing certain security criteria or safety criteria to the actual hardware access. So we can have other processes sending messages to it, and since we have some sort of functionality in the GPIO proxy to take care of these, hopefully this won't cause a problem in our system. So the GPIO proxy concept replaces the locks that we have in the traditional sense of embedded design. It does provide you with access control and mutual exclusion. It can be used to implement safety constraints. So the problem I was talking about earlier, the toggling rate of a pin, for instance, you can create some sets of rules within the proxy so that you won't damage the external hardware that you're controlling. So again, this further simplifies the application code because you're taking away those safety criteria, etc., and putting them into a central unit. You're reducing the number of lines your individual GPIO access modules are, and in effect that makes testing easier. And since you probably can use the GPIO module elsewhere in another application using GPIO, you can reuse that bit of code. Instead of having to dig it out of the existing application modules, you can abstract it into its own actor. And that's okay, we can do that. On the Raspberry Pi, just out of interest, Ed and I, we were able to create up to 136,000 Erlang processes. So a few extra processes won't hurt, you can do that. So we can further abstract this notion of proxies and hardware access modules and create platform agnostic high-level APIs that can be used in other boards as well. So far we've been talking about Raspberry Pi specifically, but say if we had let's talk about the GPIO module. So we have a certain set of operations that we can do on the GPIO pins. So we can initialize a pin as an output or an input, we can write to it, we can read from it, and perhaps we can use the interrupt capabilities of the pin. So this is our component API, and even if you go to a completely different architecture, let's say you go from an ARM architecture to a MIPS, the chances are you still will be using these primitive sort of operations on the GPIO pins. So in essence, this is a platform agnostic bit of your application. And you also have, for GPIO, you directly control hardware registers. But say if you had a temperature sensor that connected to, say, an I2C bus, now you have another layer of abstraction that you have to get through before you access hardware, and that is your I2C bus. Again, the I2C bus will give you a primitive set of operations, and they won't change between platforms. So this, again, is a platform agnostic layer that you can use in your applications. Finally, this is, unfortunately, platform specific. The actual bit of code that either twiddles registers or sets certain memory addresses to certain values, this will be hardware specific. But if you follow this layered model, what that means is majority of your applications could be ported across different architectures quite easily, since the platform specific bit is only the very bottom layer that does nothing than set registers essentially. So the temperature sensor example I've given you earlier, If you're on Linux, we can just use the sysfs, and on top of that we'll have our I2C bus driver and the sensor API. If you were on BSD, we could jump to use syscontrol. Or if you're on, say, a MIPS platform that doesn't have sysfs or syscontrol drivers, we can map memory and twiddle bits directly. We can do some register voodoo. So what's common here is the blue boxes there. They don't need to change when you're moving from board to board. So this gives you quite a platform agnostic way of creating your applications. So that was just a very simple example, the GPIO. This is a real block diagram I got from Texas Instruments website. When you're dealing with this many modules, these are all different hardware modules, by the way, you sort of really can use this model of abstraction in your complex applications. And yeah, only when you get to deal with these sort of complexity that you truly appreciate how this model can apply to your system. And if you're an embedded engineer, the chances are you will have to deal with these sort of things in the very near future, because this is where we're heading. These sort of complex system-on-chip devices are the future, unfortunately. Or fortunately, because they're quite exciting. They have multi-core processors and DSPs and all sorts of stuff in them. We are also working on an interesting bit of project called the Erlang Embedded Training Stack. So this is a complete package for people who are interested in developing these connected, distributed, embedded systems using Erlang, essentially, which gives you all these high-level features that you can use in your systems. But we're coupling that with the low-level stuff, so like the Linux device driver frameworks or direct hardware access in Linux and so on. And we're working on common hardware platforms, which is also included in this training course that you can take away and develop more applications on. So this is just in the idea phase at the moment. If you're interested, talk to me or Torben, and we'll be happy to hear your comments on this. So I think that's about it from me. Thank you very much for listening, and if you have any questions, I'll be happy to hopefully answer them. Thanks.
Novelties, know-how, and networking.
And networking.
So, feel free to help yourself to some more beer. All the little goodies are out there. Please feel free to have a look. We've got t-shirts, we've got laptop bags, we've got beanie hats, we've got loads of stuff. So feel free just to help yourself to what you want. And if there's anybody within the room that you feel might be able to help you with a question or an answer, feel free.
Thank you.